Good morning. This is Jenya Tabisola from 3IND2 presenting my research topic proposal, Water Sponge Controlled Irrigation System for Rice Farms in Nueva Ecija. Nueva Ecija. The province of Nueva Ecija is a landlocked province in the Philippines located in central Luzon region. Its capital is the city of Palayan. The province is the largest in central Luzon, covering a total area of 5,751 square kilometers. Its terrain begins with the southwestern marshes near the Pampanga border. It levels off and then gradually increases in elevation to rolling hills as it approaches the mountains of Sierra Madre in the east and the Caraballo and Cordillera Central Ranges in the north. Nueva Ecija is the center of agricultural research and production in the Philippines. It is known as the Rice Bowl of the Philippines, with rice, corn, and onion as its main agricultural products. The area also grows mango, banana, eggplant, and garlic. Other economic activities include cattle, poultry, and fish productions, investments in trading, manufacturing, and agriculture-related enterprises and products for export. Nueva Ecija shared the largest number of farms in central Luzon, with a total of 119.1 thousand farms which utilized 196.4 thousand hectares of land for agriculture. Also the biggest among the provinces. About 34.9% of the total number of farms and 35.6% of the total farm area in the region were accounted by this province. The average farm size was 1.6 hectares. A watershed commonly known as a dam can be located in this province. The Pantabangan Caraballo watershed bounded on the north, northwest, and northeast by the Caraballo mountain ranges and the south, southeast, and southwest by the Sierra Madre ranges. It is in the municipalities of Pantabangan and Caranglan in the province of Nueva Ecija, municipalities of Alfonso, Castañeda, and Dupax del Sur in the province of Nueva Vizcaya, and the municipality of Maria Aurora in province of Aurora. The watershed is approximately 176 kilometers away from Manila. The Pantabangan Dam stands as a feat of Filipino engineering phenomenon, providing ample power source, irrigation, and potable water to all the towns in the province of Nueva Ecija. The Pantabangan hydropower plant supplies 112 MW in addition to the 150 MW generated by the Kaseknan Multipurpose Irrigation and Power Project for province's energy consumption needs. The Pampanga River, which runs across the province of Nueva Ecija, also provides the irrigation to the rich farmlands, generates hydroelectric power, and minimizes flood damage to the area. However, according to the research of Rodel Lacso and his team, even if the Pantabangan Reservoir is in these areas, it only acts as an host for irrigation water to the central Luzon area. Farmlands are unirrigated because of the topography. Hence, farmers are mostly dependent on rain and deep well sources. Another contributing factor to the water scarcity in the agricultural sector of Nueva Ecija is the El Nino phenomenon. Severe water scarcity in the Philippines began in 2015. El Nino triggered a severe drought that affects everyone, especially the Philippines' agricultural sector. The Department of Agricultural Sector in 2019 forewarned that there has been a declining water supply for agriculture over the last decades, and that the El Nino weather phenomenon and the mismanagement of the Philippines' water natural resources will lead to an agricultural crisis. According to the study of Can and his research team, El Nino phenomenon is a unique occurrence once in every 2 years. This phenomenon occurs when the surface water of the equatorial Pacific's temperature becomes warmer than the desired median, and the east wind blows inadequately than normal. In the Southeast Asia, El Nino brings drier weather and causes droughts in most areas across the region. While according to Roberts and his research team, Philippines suffers a greater deal of impact on the agricultural sector when El Nino occurs. This causes a production shortfall, causes many large increases in Philippine rice prices, and lowers the quality of the rice production in the aftermath. According to the research of Chapagain and his team, The challenges in water source combined with the central lives and income of the independent farmers and their families and the high necessity of water requirements emphasizes the great need of improving the productivity in rice farming. However, in the Philippines, despite the importance of irrigation system in context with water scarcity, there is a slim number of studies, assessments, and innovation for irrigation systems for rice farm. The current irrigated lowland farms in the Philippines require a large amount of water. For example, to produce 1 kilo of rice needs an average of 3,000 liters of water. With this in mind, climatic changes such as El Nino phenomenon aggravates the water scarcity situation that gravely affects the agricultural sector of the Philippines. To address the problem of the exacerbating water scarcity, researchers have developed water-saving technologies. One of these technologies and techniques is controlled irrigation, where direct drying, wet seeding, land leveling, and alternate wetting and drying. The controlled irrigation technique necessitates a systematic scheduling of irrigation that depends on the cooperation among the farmers. Another issue that adds to this dilemma is that in the past techniques, farmers rely only on deep well water sources, government issued water source, or rainfall water. These methods of collecting water for irrigation cannot adapt and proven to be unreliable in the changing world due to the drastic climate changes brought by the growing problem of the global warming. For example, in Nueva Ecija, just 8 months ago in Pantabangan Dam, rose the old town that was purposefully drowned in water to make the dam. There have been already 17 times that the old town have risen. However, the most current rise of the town shows a grave sign that the Pantabangan Dam has a low water level than it should be, since the area of the old Pantabangan town that had risen is wider than the normal. The normal should only show the crucifix of the old St. Andre parish. This shows a sign that the water levels of the dam will eventually not suffice the requirements of water the agricultural sector in Nueva Ecija needs. A research and design development conducted by Kim and his team in 2017 showed that it is possible to harvest water from the atmosphere using metal organic frameworks, which are mechanically engineered molecules. The first type of MOF developed to collect water was called MOF 801. However, this device can only harvest 2.8 liters per kilogram of water under a non-concentrated solar flux, requiring no external power source for producing water at ambient temperature outdoors. However, in the recent advancement of Yagi and his team of scientists for MOFs, they developed an MOF called MOF 303 that is based on a cheap and abundant metal source, aluminum. They developed a water harvester that can be used anywhere in the world for the towns of the Arizona desert that can supply 22,500 liters of water with the help of a heat generator powered by a solar panel. With this advancement of nanotechnology, new sustainable innovations can be developed in the Philippines to help the scarcity of water in the agricultural sector. This study seeks to answer the following questions. How do the water sponge controlled irrigation system be designed? How do the water sponge controlled irrigation system be developed? How much water can be collected using the water sponge controlled irrigation system? What is the design plan of the water sponge controlled irrigation system? How can the water sponge controlled irrigation system disseminate the water collected? This study aims to determine the design plan of the water sponge controlled irrigation system, describe how the design functions, develop a scaled water sponge irrigation system, design a water dissemination system for the water sponge controlled irrigation system. Theories used. The is systematical in a sense that the design uses a system that can harvest water from the natural resources to irrigate rice farms and disseminate the water harvested. The design also covers the scientific part of this theory in a sense of how the water is harvested using the scientific process. The design and development of this study will be different in a way that the method and water source will not be coming from the normal water source, such as the government-issued water source, river banks, and deep well water source. The design will have a detailed requirements in its system to harvest water that will give an extreme value to the irrigation system of Nueva Ecija rice farms. In the design of this study, not only will the WSCIS harvest water from unconventional water sources, but it will also have a system that will irrigate the rice farms with a specific method and the storage area for the collected water. Methods used. The engineering design process. First, we will identify the problem, then do a background research. Then we will list down the appropriate requirements for the solution. Next is to formulate a solution. Lastly, develop a design plan. First is to implement the solution. Next is to gather feedback from the participants, have an outcome, and lastly, determine the impact of the solution to evaluate if the solution is efficient.